Hi everyone, my name is Johan Dufresne, and today I will present you the paper that we submitted this year to WABI, and that is called a graph-theoretic barcode ordering model for linked read. So first of all, I will talk a bit about linked read. What is linked read? What are linked reads? So most of the time we talk about second and third generation sequencer. So the second generation sequencer allow to sequence genome on short reads with a low error rate, or third generation are producing sequence of long reads with high error rates, except for the IFI techniques. Here we will focus on linked read, and linked read are sequencing techniques first introduced by 10x Genomics, and that remain in between. We are simulating long reads with short read sequencing, but with tags. So first of all, what exactly are linked read? So the linked reads, for linked read sequencing, you take the complete genome, you split it into multiple long reads, and you physically separate them into beads or area, physical area. And for each long read, you add one barcode. Here, the barcodes are represented by the colors. In each area, physical area, you have a long molecule that is amplified, split into short reads, and each short read is hybridized with the local barcode here. All the short reads are hybridized with a yellow barcode, and all are coming from the same long molecule. So because of the physical distanciation of all the long molecule, we can guarantee that all the reads that are coming from the same long molecule are tagged with the same barcode. But because of the limitation on the number of barcodes, one barcode can be used multiple times. And so two long molecules can end with the same barcode. Here is a list of a few softwares that are developed for this kind of technology. We have read mappers, assemblers, or variant colors, etc. And particularly, we have Minerva, that is a software that aims to separate short reads into their originate molecule. But Minerva has some troubles because they are separating around 10% of the reads. So the second part will be on graph models that are linked to linked read. So a quick reminder of linked read. So you have the genome, you split it into long reads that are barcoded. Each long read is sequenced by short reads that share the same barcode. And you sequence all the short reads together, and you have a bunch of short reads with barcodes. But here on this example, you have two long molecules on the left and the right that share the same barcode, here the violet. So you can differentiate the short reads where the pointer. You can differentiate here the short reads that are coming from this molecule or this molecule. Our goal here is, first, we want to know, can we count how many molecules were assigned to each barcode? And the second question that we want to tackle is, can we reconstruct the order of the long molecules that are behind the short reads that we sequenced? Now I will show you the two kind of graphs that are linked with the technology. Here, first, that we call the molecule graph. So each node in the graph corresponds to a long molecule, and each edge corresponds to an overlap between two molecules. So here, if I add a third molecule that is tagged in red, it overlaps the white and the blue, so we add two edges, and we can continue for the whole genome. This structure is linear, and in fact, it's an interval graph because molecules are segments that are all along the genomes. The second graph that I want to introduce is what we call the barcode graph. Here we are not focusing on molecule, but on barcodes. Each node is a barcode, so here there is the white and the blue, and because one molecule with the white barcode overlap one molecule in the blue barcode, we add an edge between the two barcodes. When we add the third barcode with a molecule that overlap the two other, we add two edges, etc. Each we reach another molecule that share a barcode with a previous molecule. So here it's the blue barcode, and this molecule here overlap the orange and the black barcode. So the blue barcode overlap the orange and the black. So the blue barcode overlap the orange, and we have to add a new link, not a new node, because we already have the blue barcode. And we can continue for the all barcodes, barcoded molecules. This graph is an intersection graph that is a generalization of the interval graphs. Here in the strategies that we propose to order the barcode. First, we take all the barcoded short reads, we create from them the barcode graph, and from the barcode graph, we try to realize the molecule graph. This is the third part of this talk and the fourth part of this talk. Before to tackle the problems, I want to go back to some results, some previous results on computer theory side. So the first result it's about the interval graph. The interval graph is what when you have exactly the interval in each for us. It's when you have exactly the molecule in each barcode colliding with the same barcode. So there is a proof that the two interval graph recognizing it is NP-complete, and there is no results on larger graph, but it seems harder. On this kind of multiple interval graph, we have the max.cliques that is NP-complete, and for ordering problems like the ones that we are trying to do, there exists integer linear programming, but they don't scale on genomic size problem. So now let's go to try to realize a molecular graph through a barcode graph. The molecular graph is, when it's well balanced like that, it's composed of max.cliques that are all of the same size. If it's not well balanced, it's cliques that are not of the same size, but still cliques. And you can traverse the graph by jumping from one max.clique to another one. It's tractable on interval graph, but it's NP-complete as we just saw, but we still can compute them locally and it can be tractable. But the main problem is that we simulate a bunch of barcode graphs And in fact, the max-clique into the barcode graph are not corresponding to the max-clique of the molecule graphs. So we want to introduce a new structure that can undercover the molecule graph. We call it local clique pair. It's still based on cliques. So you center on one node, you extract the neighbors of the node, and on each side, if you are on an interval graph, on each side you have one clique, and the cliques are linking together with what we call clique linking edges. This kind of structure are the same properties that we can jump from one to another just by adding one node on the right and removing one on the left. So this is a good point. But it have one more property that the max-clique don't have, is that when you have your molecule graph and there is a collision between two barcode, the fusion graph will keep a kind of orientation. We still have, using the linking edges, we still have an idea on how many different molecules are inside of this barcode. Here I will present you a metric on how to differentiate good and bad local clique pairs. So the ideal one is this one with balanced cliques and edges, linking edges that are going from the left clique to the right clique. This one is likely artifactual because there is no link between the two cliques. And in fact, we are introducing a weight that is how many red edges, so linking edges, we observe regarding how many we are expecting. So here on this example, we are expecting 3 edges and we see 2, so the weight is 1. So if we are 0, if the weight is 0, it's a very good LCP, and higher is the weight, badder. I don't know if it's like that, but the high weight are bad. In our barcode graph, we now can try to retrieve all the LCP. So we can focus on one node because LCP are local. So we can extract the induced subgraph and compute locally the max cliques. So here there are 4 cliques. And you can, as you can see here, the red and the blue cliques share one node. You compute the weight of the clique pairs. You can invert them because I want to maximize things just after. So you do the maximum weight minus the weight of the edge. And you can perform a maximum weight matching. So a maximum weight matching is when you are trying to pair nodes in a graph, maximizing the sum of their edges. So here we have two local clique pairs, the red and the red yellow and the green blue. And in fact, what we see using that method is we see a kind of soft clustering because this node is part of the two LCPs here and here. Here again, I will present you another kind of graph, but this graph is not relying on the sequencing technique, but on our resolution. So we can enumerate all the LCP on the graph, on the barcode graph, and this LCP become the nodes of what we call the LCP graph. and we can compute the symmetry difference between all the nodes of the LCP graph and only keep the values that are low. We have now the LCP graph. We can try to extract a path from this graph, because if we can extract one complete path, we will have the order of all the barcodes that are along the genome. In fact, we want to travel the graph with the edges that have low values, because there is no many difference between the LCP. So first, we simplify the graph by transitive edge removal. Then we are performing a local branch and bound algorithm to create the LCP graph. For that, you can read it in the paper. And finally, we extract the central node of each barcode of each LCP to transform the LCP path into a barcode graph, into a barcode path. Here are two experiments that we did. We have more experiments in the article, but these two are the two most difficult ones that we presented into the article. One with 5,000 molecules, the other with 10,000 molecules that are merged with around three molecules in each barcode on average. We did three measures. We computed three measures. The first is based on a random walk. We created at random path of length 100, and we are looking at the barcodes in this path, are they corresponding to the correct order of barcodes all along the genome. And in 95% of the random path here for the 5,000 and 99% on the 10,000, yes, they are corresponding to the real order of molecules. Sensitivity is, sensitivity on the LCP graph are we able to find the full path, or how much of the full path are we able to retrieve in the LCP graph? So here we can reconstruct at most 99% of the original genome. And finally, the sensitivity of our heuristic is how much of the original path our heuristic reconstructed. So we reconstructed with a naive heuristic almost 90% out of the 99 possible. To illustrate that, I want to show you this barcode graph that is corresponding to the, I think, 5,000 molecules. And here on the right is the LCP graph that we created. It's very, very linear, and it looks like an almost complete genome. The second part, that is the first part in our process, is how to construct our barcode graph from the reads. So first, we have all the reads outputted from the sequencing for all the short reads from sequencing, and we are creating an assembly using spades. We have a bunch of contigs, and using linked read mapper like EMA, we align all the reads along the genome. We then infer long molecule from the reads, and we infer the barcode graph from the overlapping of the inferred long molecule. And this is very good. In fact, on our E. coli test, we did not create, we create almost no wrong edges between the barcodes. So almost all the barcodes are, all the edges are correct, even if we missed around 10% of the edges. But 10% is good. And right now we are here and we are trying to scaling up our algorithm to construct the LCP graph on real data, because when we have real genomes barcode graph, we have local dense clique areas. And for that, we can't create LCP paths for now, but we are scaling up. And we want to use this technique, the technique that I just presented, as a first step of deconvolution, because if we already know how many molecules there are for each are present in each barcode, we can give that to clustering algorithm, and we can apply the second question on scaffolding for genomes and metagenomes. What I want that you remind after this talk is that we present two graph structures that are linked to linked thread, and we presented how to construct them and a few algorithms on how to create the molecule graph from the barcode graph. And there is still one step to go to the full deconvolution problem. And finally, I want to thank all of my co-authors and collaborators. If you have any question, I'm right now available for question online or after on Twitter if you want. Thanks.